This
team.
conference will now be recorded.
So is everyone seeing my screen okay?
Yep.
All right, fantastic. So as was indicated, I will be speaking on the evolution of drive motor technology and how we're addressing increasing demand for higher efficient motor technologies. So this that we'll be talking about today, you can kind of refer to it as a ferrite assisted, and ferrites are magnets, synchronous reluctance motor. So the synchronous reluctance relates to the rotor design that you see in the picture on the top, and it has internal ferrite magnet material. And really just at the core, the idea is simple. You want to design this using a proven stator technology and then use an innovative rotor design to achieve the high efficiency. And the reason you want to do that is that maintains the standard simplicity, service-friendly capability and drop-in ability of just a standard NEMA rolled steel motor frame and technology. So without doing anything too exotic. But we'll be actually discussing the different technologies that have been applied to address the high efficiency requirements in the marketplace. Again, thank you for the introduction. I am Mark Dimitro, product manager for Variable Speed Motors. That is me without the beard. I am now fully bearded. So, and I think it's here to stay. The family likes it. And I tried to shave last year and they didn't recognize me, so it's back. So why is this topic important? I mean, if you think back to 2016 when the Department of Energy mandated NEMA premium energy efficient motors, there was a lot of topic, a lot of conversation on energy upgrades and going to higher efficiency motor products. And then it kind of was on the sideline there for a little while. Well, it's back, and it's back in full force. And the reason being, motors consume about 1/3 of the world's electricity, and that number is not going down. It's expected to double by 2040. Put it in perspective, that's equivalent to adding the electricity market the size of China to the grid. And as you know, power plants, adding new facilities isn't particularly easy a lot. So one of the easiest ways to increase your generating capacity is to reduce the demand. And if 1/3 of the electricity being consumed that you produce is electric motors, well, that's a good place to start. Especially when 70% of all those motors that are consuming that electricity are used in industrial applications, and then near and dear to what we're talking about here today, and heating, ventilating, and air conditioning systems, building automation. That accounts for 38% of all the energy that's used in industrial applications is right there in HVAC systems. So it's a sizable chunk of the processes and the electricity consumed by electric motors. So there's a lot of renewed interest on how can I get to a higher efficiency level with my motor and with the entire system design. So, fundamentally, we're going to be talking about motor technology here today. However, I would tell you that the biggest contributor to system efficiency is the design of the pump or the fan in and of itself. And what I would tell you is, you want to pick a motor product or technology that when you apply it to that pump or that fan is going to give you as much flexibility as you possibly can to innovate on the design of the fan or the pump, because that's really going to get you your highest efficiency level. And so again, that's why this motor technology that we're talking about is built into a standard induction motor frame so that it can kind of drop in where standard premium energy efficient motor is today and provide that flexibility, right? The other aspect of it, and if you're looking at this and go, well, what does this say? You talked about energy efficiency, you talked about energy efficiency in building systems. Why is it so pertinent that pump systems, fan systems, and compressed air systems are the primary consumer of electrical energy within those systems? Normally, when you talk about efficiency for a motor at least, you talk about it at full load and full speed. But as you know, pumps, fans, and compressed air systems, at least the recirculating fans and compressed air systems, do not operate at full load and full speed. They're designed for peak capacity, but most of the time they're running 80% speed or lower. 80% speed is 52% load, and it could be even lower than that. So what you really want to look at is, what kind of efficiency gain are you getting at those partial load conditions? And that's where you really get these big paybacks. So I'm going to actually show you real world test results at the partial load conditions. But instead of a couple points of efficiency difference, you're going to see with the technology much higher efficiency differentials up to 16%, because this motor design gives you more flat efficiency performance when you're running at slower speeds and at partial loads. So here are the motor technologies that have been kind of applied into industry today to address the higher efficiency. I've already talked about standard induction motors and premium energy efficient motors. It's a familiar and proven technology. It starts across the line. So that's a really big advantage, because you don't need to have a variable speed drive on that. Although as you know, if instead of doing mechanical dampers or valves or throttling control, when you put a variable speed drive on it, you can save a considerable amount of energy. So it's debatable whether running across the line is a big advantage when you're talking about trying to save energy. It's probably better to put it on a drive. All of these other technologies that you see going to the right are to address going to higher efficiency technology. Synchronous reluctance motors, or center RM motors, are basically one of the first technologies that came out. And the whole idea in a motor is the only way you're going to get to higher efficiencies is you have to eliminate losses in the motor. And there are two fundamental places you get losses in the motor. It's either in the stator windings due to resistance and losses putting current through the wire, or it's circulating I²R losses in the rotor. So what a synchronous reluctance rotor does is it puts air gaps into the rotor that channel the magnetic lines of flux and they basically produce a no loss rotor. And when you reduce the losses in the motor, the losses in the rotor, it eliminates about 20% of the losses overall, which boosts you from an IE3 motor to IE4. If you're not, IE is a IEC standard. If you're not all that familiar with it versus NEMA, the reason we use it is because NEMA really only has a standard up to what we call IE3. That's a premium energy efficient motor. There's terminology being used out there for super premium, which would be like an IE4, and ultra super premium, which would be like an IE5 motor, but there's really no NEMA standard for it. And the IEC scale from IE3 to 5, there's actually a scale, so we kind of default to using it because there's no NEMA standard. Synchronous reluctance motors also have no magnets in them. So a lot of these other technologies over here to get to the higher efficiencies add magnets. And you add magnets basically to do some of the work of the stator. So remember I said you got losses in the rotor, you got losses in the stator. If the stator doesn't have to work as hard, there's less losses in the stator, and that's what the magnets do. So I'm sorry, I've got timings in here for some reason, so it keeps jumping around. But if I can do some of the work of the stator with a magnet, that means that the stator works less hard, which means there's less losses in it, and I get to higher efficiency. So really electrically commutated motors, which is really a DC permanent magnet motor, interior permanent magnet motors and this motor that we're talking about here all add magnet material to reduce the losses in the stator and get you to higher efficiency. Synchronous reluctance motors do it all just with basically active material in the stator and a no-loss rotor. So it's good, except active material means the motors are typically larger. All of these from here, from the left over, except induction, require a drive, but they have lower power factor, something like 70%. I mean, you have to run it on a drive, so what you're seeing from a power factor standpoint ahead of the drive is still very good, but the low power factor of the motor means that motor typically draws more current. And so if it draws more current, it's a larger, heavier motor than typically these over here. The next one, this one's been out for a number of years. It's an electrically commutated motor, and they're sold typically as just a package. So they're not usually sold just as the motor. They have to have a drive on it. It's a DC permanent magnet controller, and they're usually sold as these packages. So you'll see them provided as the complete fan assembly. It's like a pancake design. And they are high efficient, IE4, some of them now are IE5. They're DC. DC is simple technology. It's easy to use and maintain. It's well recognized in the market. It's compact and lightweight and a simple control. But it requires a DC power rectifier, and DC rectifiers are inherently inefficient at light loads. So one of the disadvantages that, remember, you're trying to get a flat line efficiency profile at light loads. So if my rectifier or drive is inefficient at light loads, that increases your losses. And so these tend to be a little less efficient at lighter loads than what we'll talk about here with the ferrite assisted motor design. Also, they're provided as complete assemblies. So they're usually not like just the motor, which is individually serviceable. I mean, if these fail, you have to replace the whole fan, motor, and drive assembly. And historically, they've used what's called rare earth magnet material. So if you're not familiar with rare earth magnets, it's neodymium boron iron. They're rare earth because that's just the type of magnet material that they're made from. The biggest issue with those is that they're only available or mined in, I think like 80% of them come out of China. Nothing inherently wrong with that, but that provides a lot of volatility on the commodity market. These are the same kind of magnets that are used in electric vehicles, solar cells, they're in your cell phone, wind turbines. So they're really in high demand and supply is limited. So, you know, basic supply and demand, commodity volatility. So they tend to fluctuate, and you've seen it with all the supply chain issues lately, they can be hard to source too. So this design uses ferrite magnets that we're talking about here today. And a ferrite magnet is like a ceramic magnet material. Think your refrigerator magnet. You know, when you go to these guys and you say, I need ferrite magnets, they go, how many hundred thousands of pounds do you need? I mean, they're very readily available, price stable, and environmentally sustainable. So, and someone asked me one time, like, well, you know, why doesn't everybody use ferrite magnets? Well, because rare earth magnets, like if you look at this interior PM motor, how many magnets I got? 1, 2, 3, 4, 5, 6. You got 8 magnets in that motor. How many I got in here? Probably 32 or so. They're less powerful. So you need a lot more magnets in the motor. So they're typically only practical in the lower horsepower range. While, or if you want to get a very small power dense motor like this EC motor over here, because you don't have to use much magnets at all. The advantage of an interior PM motor with a rare earth magnet is it's probably the most efficient motor you can get. It has really high torque density, excellent torque to inertia ratio, high power factor, really good partial load efficiency and low noise levels. And then you're probably like, well, why isn't everybody using these in HVAC applications? Well, they're really high cost. They're difficult to service because the magnets are extremely strong, and they have high back EMF voltage. Basically, when you drive them in reverse, they turn into a generator. And because the magnets are so strong, they generate a lot of voltage, and that can be a safety concern. And they're really expensive. I mean, they're cost effective when you get like 30 horsepower and up. But the whole point of this ferrite assisted synchronous reluctance design is to get you a product that's more typical in HVAC applications, 30 horsepower and down, and more cost effective. So the ferrites are more economical and practical at the lower horsepowers, and that's why it was incorporated into this design. Again, by adding the magnet material, it improves your power factor well above 90%. Power factor can be as high as 98% at like a 10 horsepower range. And you're like, well, okay, so what does that do? Well, it drops your current draw. And if I have a lower current draw, the motor doesn't thermally heat up as much. So that's adding less heat into your airstream that you have to make up for in an HVAC application or transferring to a pump system. But it adds to the reliability. People want reliable products in HVAC systems, and the cooler the motor can operate, the longer thermal life you'll get out of the insulation system and the bearing grease. So it gets you a more reliable, cooler running motor. The other advantage of it is you can usually drop a frame size. So if a 10 horsepower was in a NEMA 250 frame, you could do this motor design in a 210 frame. So you could, get a smaller, lighter weight motor, and that might help you with your structural design. Maybe it doesn't need as much support. It may help you if you're doing retrofits, because somebody, two people might be able to rig in a 210 or a 180 frame motor, but a 250 might be too heavy. So, it helps with that. But it is a synchronous reluctance motor. So it runs at synchronous speed, and it has magnets, so it won't run across the line, and it does require a variable speed drive. So that's still a disadvantage over maybe induction that'll run across the line. So that's all the technologies out there. We're kind of focusing on this one next, on the technology. I've kind of covered some of this again that I already talked about. Phasar stands for ferrite assisted synchronous reluctance rotor. And so I already talked about what is a synchronous reluctance rotor, but it basically operates on the same principle as a induction motor, because it has a standard induction motor stator. So it gets rotation the same way a induction motor does, utilizes a standard induction motor winding. And then here is a synchronous reluctance rotor, and you can see it has air gaps here. And what the air gaps do is they channel the magnetic lines of flux through the conductive path. And so you get nice, clean magnetic lines of flux instead of getting circulating currents in a solid core rotor. And that basically eliminates the losses in the rotor. But we already talked about the low power factor. So the Phasar motor with the ferrites adds magnet material here into those air gaps, boosts your power factor up. It drops your current draw of the motor, and it does a lot of the work of the stator. So it basically does about 30% of the work of the stator winding. And so that's what reduces the losses in the stator and boosts efficiency. But remember, the whole point here isn't just to boost efficiency, it's to get you better partial load efficiency. And the no load current of an induction motor can be as high as 35%, which means it's drawing 35% current no matter what the load is. So if you're at 25% load, you're drawing 35% current, and you're getting 35% of the current losses in the stator winding. Since the magnets do about 30% of the work, if I'm at 30% load, the stator isn't doing anything, which means there's no losses in the stator. which that's why you can maintain a really flat efficiency profile. All right. So again, here's what we already talked about. So you got increasing magnetic lines of flux, torque per amp as you go left to right here. You can see these nice, clean, circulating lines of magnetic flux through the air gaps versus the circulating currents over here. And graphically, this just shows you have your rotor losses in the standard induction motor. You eliminate those losses, which is about 20% of the motor. So again, each class of efficiency is 20% less losses in the motor. So if I eliminate 20% of the losses from the rotor, that's where I get to IE4. And if I eliminate 20% more of the losses with the stator, that's where I get to IE5 by adding the magnet material. All right. So, fundamentally, that's how this technology gets you to a higher efficiency level. There's other design features into these types of motor construction that a standard induction NEMA motor allows you. And they're really, based on HVAC applications, expect longer motor life and maintenance-free operation. So you better design the motor in addition to being high efficiency with the rotor design so that you don't have unexpected downtime or maintenance issues. Also in HVAC systems, noise is an issue. So, from a design standpoint, you want to do a low noise fan and cover on there, smaller fan size on it. And that's the other thing. So if you think like, well, what does a cooler running motor also get me? Well, it's a class B temperature rise in these systems. The standard induction motor is class F rise. So they run about 20% hotter. So that's shorter life in your insulation system. That also degrades your grease life. And by having a class B temperature rise, you can also put a smaller cooling fan on these, and that's why they run at a less dBA noise level. So it gets you a quieter motor from a design standpoint too, because you can capitalize on these lower temperatures. The IP54, pretty much anyone can do that with any of those motor technology. I just put it in here because that's kind of the standard. IP55 in IEC, IP54 for HVAC applications, just to seal up the motor and provide you a design that you don't have to worry about dust and light condensation that's going to take out the motor. Again, it requires a drive to operate, and because it requires a drive, we recommend having a shaft grounding brush on here or ceramic bearings, and that's basically to deal with electrical discharge. So when you have a drive on a motor, you have capacitive coupled currents and common mode voltages that can cause shaft discharges, and that basically pits away at the bearings and cause premature failure. I'll show you a graphic of what that looks like. So this motor design has that as standard, but it's highly recommended for HVAC motors, any design. If you're going to put it on a drive, from a safe system standpoint, either electrically isolate with ceramic bearings or do a shaft grounding brush. I like shaft grounding brushes because it takes any of that common mode voltage and current and shunts it right to ground. A ceramic bearing electrically isolates the bearing and protects the bearing, but that current still has to go somewhere, and it's going to go into the driven current. Now, if you're on a floating shaft fan blade, that's not a big deal because it's going to find the shortest path to ground, and that's going to be through the motor frame. But if you're on a pump or something, it's like you got to ask yourself, where did that voltage and that current go? And this is what it looks like. So the VFD switching frequency creates parasitic capacitance between the rotor and stator, and that capacitance induces a voltage. And this is that voltage you see here. And it's kind of like the electrical globe science theater thing. If you have a big enough voltage potential between two conductors, you'll get an electrical arc that'll actually discharge across that electrical arc. So it's like the old sci-fi movies where you see those little bulbs and electrical arc. It's really no different. You ionize the air between the two conductors, and you have a little mini lightning bolt. And that little mini lightning bolt literally anneals the bearing races, makes them brittle, and then they pit out and cause your bearing to fail. So this is before a shaft grounding brush, and this is after. It basically takes all this and shunts it to ground and removes it from the system. And that's why they're recommended. This is what IP54, if you're not familiar with the testing, it's actually a lot more severe than you would typically see in an HVAC system, but it's kind of gets you your worst case. You know, hey, if it's a condenser fan motor, or it's outside, or there's a lot of dust in the air, then that's why it is. So basically what you do is, this is a little vacuum hose. You have to attach a vacuum hose, you put it in the dust chamber, you pull a vacuum on the inside of the motor, and no dust can get on the inside. And then the water test is, you actually put a white dye inside the motor. It reacts to water and turns a blue color, and you put it in the spray chamber, and it's just like garden hose pressure, so it's not like high pressure, but none of the water can get inside the motor. And so that's what gives you, again, for HVAC systems, it's recommended like IP54 as a standard to just protect the product. But it's, you know, probably a higher integrity than you're going to see in every application, obviously. This is just an actual, like, you're like, oh, sure, it runs 20% cooler. Well, so I just wanted to show you, this is the actual thermal testing on the motor. So you got an induction motor, 84.2 C. Here's the phasar motor running in a lab thermal imagery, 68.2. So it's over 16 degrees cooler. And so that equates to about a 20% cooler running motor. This was only a 3-horse motor, so they just don't draw a lot of amps, but you can see an induction drew 4.27 amps. This design, because the magnets, is doing 3.72. So high power factor, lower amp draw. In certain cases, the advantage of this is sometimes it'll allow you to do a smaller drive on it. You know, it depends on where the cutoff is, but you know, you may have had an induction motor, 10 horsepower, that you had to put you might have to put a bigger drive on this induction motor than you would on this phasar motor design, because it's drawing less amps. All right. And then this just shows, like, an electrically commutated motor. DC motors do draw low amps, have good power factor, system efficiency, and temperature. So basically what a phasar motor does is it gets you right in line with electrically commutated motors from efficiency at full load and speed, performance standpoint, and temperature. You know, one of the things DC motors have touted over induction. So I'm not going to spend a lot of time on this because I already talked about that. This just shows you where the neodymium boron iron magnets come from, 78% out of China and a few other parts in the world. And that's why, you know, from a magnet technology standpoint, a lot of companies, even EC motors, are out there looking at redesigning to ferrites for the same reason. So it's something to look for in a motor design, because if you're still using rare earth magnets in these low horsepower motors, you might get into a situation where, because of commodity or supply chain issues, that you can't get the motor because you're still using rare earth magnets. So that's why this design uses ferrites or ceramic magnet material. These are the IEC standards. Again, there's standard efficient, high efficient, and premium efficient. In the NEMA world, there's really no standard above here, although people have been calling it super premium or ultra premium. And that's why, you know, we tend to use these IEC standards, because they do actually define it. But it's not really that complicated. Each class of efficiency has 20% less motor losses, and that's how you get up to higher efficiency. There's 2 standards within the IEC world to either define efficiency classes for direct across the line motors, which is this 60034-30-1. And there's a new technical standard for synchronous reluctance motors, the ferrite assisted motors, and permanent magnet motors that have to run on a drive. and that's the -2. And it's to create a more level playing field because the newer motor technologies at higher efficiency require a drive. You can't really compare them to a direct across the line motors, but we're going to do it anyway. So here's your efficiencies. Just to show you the difference, this dotted line is the 60034-30-2 IE5 standard. That's a NEMA premium motor. That's a super premium or IE4. And this is the IE5 or phasar. And so what you're going to see here is that this magnet technology and rotor design actually achieves much higher efficiency. You'll see it referred to as IE5 plus in a lot of cases than the actual standard. And if you actually looked at a 20 horse, it's roughly 95.9% efficient. And if you did the loss calculation, IE6, which doesn't even exist, is 96.2. So it's pretty close to IE6. So it gives you a lot of headway. Even when you put a drive on it with 2% losses, it's going to be close to IE5 even with the drive. So, but I've been talking about it like flatline efficiency performance, and here it is. So this is actual lab testing data. Yes, it's prettied up to put into a presentation, but it is actually based on measured lab dynamometer testing of an induction motor versus the phasar design. This is at 100% speed and partial load points. Again, systems are designed for peak capacity and loading, but they're sometimes run partial loads. This would be more like a constant CFM system that's running at a fixed speed, but the loading's variable. And you can see that, you know, it's up to 2 times the efficiency gain at 25% loading than here at full load and full speed. And then when you look at on a variable torque application, so now you're talking variable speed and variable torque. So, you know, if I looked here at 80% speed, it's roughly, you know, 52% torque or somewhere around there. And this is your induction motor. Again, it's falling off more rapidly. And this is the phasar motor here. It stays pretty flat line on variable torque and speed up to about 50% speed and then drops off a little bit, but not as much as an induction design. And again, that's just because the magnets are doing a lot of the work at the lower torque levels and taking that work off the stator itself. So again, this was the actual lab testing data in a motor development lab. There has been customer testing on it as well. So I kind of wanted to show you a comparison of, okay, here's lab data and here's an actual pump OEM that did testing. So this pump OEM took a drive, ran it on the identical drive. They ran a induction motor. They ran an actual IE5 synchronous reluctance motor. And then they ran this IE5 ferrite assisted synchronous reluctance motor, and they ran it on their pump. So, you know, I can't really impart this highly enough. It's like, you know, I can tell you the motor does one thing, but until you apply it on the system, that's where your real benefits are. And you can see it here at their pump flow and design point, which was about 80% speed. They were actually kind of shocked in their testing because they thought, well, it'll be close to this IE5 synchronous reluctance motor, and it wasn't. They actually picked up, and this is system efficiency, so this includes the pump losses. They picked up 7.2% efficiency over an induction motor, and surprisingly 3.9% pump system efficiency over another IE5 design. And that's just really because it's holding that partial load efficiency at a higher level. So depending on the pump design curve and where it's operating, you can see significant gains over different other technologies. And then this was a electrical company. They make, it's actually in India. They're a manufacturer of capsules and films. And they upgraded a pumping system, so variable speed, variable torque system. So it went from variable speed to variable speed. So it's an equitable comparison. And this is just raw power consumption. So it's not like they went from a fixed speed pump to a variable speed and got savings that way. This was literally variable speed before. It was like an IE2-3 motor. I mean, it was India, so I'm not, they said it was IE2 or 3. They didn't know exactly. But they did the actual power measurements with a power meter. So this is real world data. They took an average over 7 days, and they used 57 kilowatt hours of energy, and so that averages out to roughly $200 over that time period. And then they measured the phasar motor, and it dropped to 45 kilowatts, which equated to, and their cost was 12 cents a kilowatt hour, $155. So that's $520, and it was a year-and-a-half payback. And that was just one motor, one 7.5 horsepower motor. So even going, variable speed to variable speed, swapping out the motor, you can see some significant energy savings and get into that magic sweet spot where everybody they want to be under 2 years from a payback analysis standpoint. So I wanted to show these because it's real world information, real world data, not lab data. It kind of just shows what we've been talking about here. The design is available now basically up to 20 horsepower as a motor only. And again, like I said, that's where the need in the market is that lower horsepower where a traditional permanent magnet motor is too expensive. And then there's a lot of initiative to kind of, we don't want to mount the drive in a control cabinet. We'd rather have it right on the motor. So you'll also see a lot of trending, like an electrically commutated motor has the drive built into it. So there's a lot of requesting for in fan systems and pump systems, especially if you're changing out an old induction motor and you don't want to worry about, where am I going to put this drive, and then what, how am I going to find a cabinet space to put it. So there's a lot of need too to have the drive mounted on the motor, either on the back end or on the top of it. So that's what I had here for you today. In summary, phasar motors meet or exceed the IE5 efficiency. They don't use rare earth magnet materials, and they combine a conventional proven stator technology with an innovative rotor design, ultimately to give you the simplicity and service friendliness of an induction motor while getting up to higher efficiency levels. So again, that's what I had here for you today, and we can go ahead and open it for questions.
Thanks, Mark. Thank you for that presentation. If you have any questions, please type in the chat box. I just have one question, Mark.
Yeah.
You mentioned the IP54. What does IP stand for? Is that
Ingress protection?
Okay.
Yeah, and again, I should have expounded on that. So in the NEMA world, there's NEMA 12, there's NEMA 1, and there's NEMA 4. The IP scale, which stands for ingress protection, is a little bit more finer detail. So there's IP 1, 2, 3, 4, 5, 6, and then the second digit from 1 to 6, and it gives you a lot more. In the first digit is how much dust protection it has, and the second digit is how much water protection. In the NEMA world, NEMA 1 is like a standard motor. NEMA 12 is like dust tight, drip tight, so it's kind of equivalent to IP54. And then NEMA 4 is higher volume water washdown, so it'd be like an IP66. But yeah, it's just ingress protection.
I do see a question. What HVAC equipment manufacturers are currently using the FASR motors?
Did you want specific OEMs, or I didn't know who you wanted? Yeah.
Just a general question, I guess.
Well, yeah, there's a number of fan manufacturers that are utilizing it. There's a couple roof-mounted air handling unit manufacturers that are looking to use it. It's being used a lot in data centers on supply and relief fans. I mean, yeah, I didn't know, with an Ashrae meeting, Sam, like you wanted to actually start talking about actual names of OEMs, right? But
yeah, so that would be a question.
But it's there are a number of so there's different segments. You've got, let's say a roof-mounted air handling unit manufacturer, and they might do the whole air handling unit, and they might have a bank of motors in there that are kind of almost like a fan wall for cooling. And there's a few of those guys that have started to use it. There's a couple of major fan manufacturers that, their primary, they basically manufacture the fans and put this motor on it, and then they might supply it to an air handling integrator, right?
Sounds good.
And it's being also dropped into a lot of data centers. So yeah, and there's a number of pump OEMs that are starting to utilize it as well. So it's been very well received.
So I have another question as well, because I'm taking an electrical class. I guess one of the things is you mentioned something about high back EMF being generated that causes high voltage. Do you see a lot of that? Like in what application do you see it, or does it just pertain to like a certain type of motor?
Well, probably like, let's say you've got a relief fan up on the roof, and you don't have backdraft dampers on it. And then if you get windmilling on the motor, and somebody comes up thinking the motor is disconnected and there's no voltage on the terminals, but it's spinning, and they touch the leads, they're going to get a shock because there's magnets in it, and it's going to generate voltage. And because the rare earths are stronger, they tend to generate a higher voltage level. So it's more of a safety concern. These are the relative back EMF voltage is lower than, let's say, a rare earth magnet material. That's not to say that you still need to be safe. I mean, it's something to be aware of. It working on any permanent magnet motor, if the fan blades are rotating, or getting backdraft air or windmilling, you're going to have some voltage on there, right? So just be careful. I mean, usually it ain't that high because it's not windmilling at full speed. It's not like it's backdrafting at 1800 RPM, right?
Sure.
But you might get like 20 volts or something. I mean, it's not going to be life threatening, but it'll give you a good jolt. So, I mean, one little service note on a permanent magnet motor: if you short 2 leads, you lock it up. So like, you'll see some systems have what's called shorting contactors as a safety backup when they work on them. So normally you don't see that in HVAC systems, though.
No, okay.
I mean, that's normal for like more like 100 horsepower cooling tower motor, let's say. where you could really have significant voltage and safety concerns. They have shorting contactors to ensure that there's no rotation and everything's safe. You know, 5 horsepower HVAC motor, it's not that big of a deal. But anyway.
Does anyone else have any questions?
AJ is correct.
Well, seeing I don't see any questions, thanks again for your presentation and your time.
I enjoyed it. I hope everybody got some good information today.
Thanks, Mark.
Thank you, everybody. You have a pleasant day.